The next skill that's part of Chapter 16 on kinetics has to do with thinking about rate laws. So remember, we can write a rate law as rate equals the rate constant times the concentration of A raised to the m power times the concentration of B raised to the n power. Again, this is a generic rate law that tells us for reactants A and B, the reaction orders M and N are as given. So you want to remember kind of this generic expression for a rate law. Now, in our next couple of sample problems, we'll work through how to actually figure out what M and N are. And a really important point to point out is that M and N cannot be determined from your equation. They might end up coincidentally being the same as the coefficients in your equation, but you cannot determine them from your equation. So we need to use experimental data. This sample problem, however, is a little bit simpler in that we're actually determining reaction orders from a given rate law. So we don't actually need to use experimental data because they're already giving us the rate law. It's important here, though, that they give us the equation as well, as we'll see in our last problem here, because reactants will appear in the rate law in all but C here. So we'll get to that in a minute, and hopefully that will make a little bit more sense. So the question asks, for each of the following reactions, use the given rate law. So again, we are given the rate law, so we don't have to experimentally determine anything. Determine the reaction order with respect to each reactant, and then the overall order. So if we look at this first reaction, again, the rate law is given as rate equals the rate constant times the concentration of NO squared times the concentration of NO. All we have to do here to solve this problem is look at these exponents, and again, these exponents tell us the order. So we can write that the reaction is second order with respect to NO, and that's how you kind of write reaction order. You can say the reaction is second order with respect to whatever species you're talking about, and because we have that exponent of a 2 there, that means it's second order with respect to that species, and the reaction is first order with respect to O2. Again, no coefficient there means that it's assumed to be a 1. How you get overall reaction order, and we should write this here, overall order equals M plus N. So the reaction is third order overall. And we'll learn a little bit in our last lecture, lecture 4, and on our chapter here in kinetics about what it actually means to be first, second, or third order in terms of a reaction. So again, this reaction is this problem is pretty straightforward. They give us the rate law, so all we have to do is look at the exponents here to determine what the reaction order is. So problems B and C kind of highlight a couple of different or interesting things that you might see with some of these problems. So if we look at problem B, so CH3CHO gas goes to CH4 gas and then carbon monoxide gas. So the rate constant is given, or the rate law is given as rate equals rate constant times the concentration of the only reactant raised to the 3/2 power. So what we'd say for this is that the reaction is 3/2 order with respect to CH3CHO. And I know that looks a little bit weird, but the important kind of point to take from this problem is that non-integer numbers are okay. All that just means is that there's not easy math to do. So non-integer numbers, okay. And as we mentioned in class, it just means that it's not math that you can do in your head, right? We can't easily say, oh, if we double this concentration, the rate is going to quadruple, or the rate is going to have some predictable, easy math to figure out. You just have to raise it to a 1/2 power to see the effect on rate. So non-integer values are okay. The last problem here, part of this sample problem, highlights an important thing and why they actually gave us the reaction equations. You might say that for these first two problems, we didn't even have to look at the reaction to figure out what was going on or to answer the question. Oh, just to highlight here, it's third order with respect to CH3CHO, and I'm sorry, 3/2 order and 3/2 order overall. So to answer both of those, because it asks for each reactant and then overall order. What's highlighted in part C here is an important thing to think about in terms of why they gave us the reaction. So if we look at the rate law that's given, rate equals the rate constant times the concentration of peroxide times the concentration of iodide. And one of the things that we see is that this guy is missing from the rate law. And what it means if something is missing from the rate law is it means that the reaction is zero order with respect to that species. So we can say the reaction is zero order with respect to protons. Now, again, to highlight what zero order means, it means that the reaction rate is independent of changes in the concentration of H+. So, said another way, this is a pH insensitive reaction. We just need to have some H+ around. Okay, but important that it does not mean that we don't need H+ for the reaction. So the reaction still needs H+ for chemistry. So it doesn't mean that we don't need that reagent. It just means that the rate is not dependent on the concentration of that reagent. And as we'll learn about in our last lecture, what it really means is that this is important for chemistry to happen, but it's not part of the slowest step of the reaction. And that'll make sense, again, as we get to that last lecture. But again, when we have multi-step reactions and we have a bottleneck and one step that's slow, that player is going to be absent from that step because it's not participating in the slowest or the rate limiting step. So again, relatively simple problem to determine reaction orders if you're given the rate law. Just look at the coefficients that the exponents that we have there, and those are going to be your reaction orders. Sum them to get the overall order. Problem B kind of highlighted that non-integer numbers are okay. Negative numbers are okay too. I think there's a homework problem that deals with that. And you're given the reaction equation because the only way that you will know if something is zero order is it's present in the chemical equation but absent from the rate law.